Okay, so I will do my presentation on multi-core debugger integration and suspend resume. Those of you who were already in the SystemC meeting last year will probably remember that I did a presentation on this topic as well at that time. So I'm now going to present, let's say, the updates and what I basically promised to improve on what I had discussed at that moment. Yeah, so my presentation is going to have the following outline. First, I'm going to present and introduce why I'm doing this, what is the background, what is the organization that I'm coming from. I'm going to discuss the problem statement in more detail. Going to discuss what I implemented and presented last year and what I found, what other people did. And then I'm going to discuss the new approach on how to do synchronization control when you have, let's say, multiple debuggers trying to control the simulation and trying to debug multiple applications running at the same moment in time on multiple processors in your system simulation. And in the end, I'm going to discuss how we could apply these concepts in a more generic way. So not only when you have ISSs in your simulations, but just more in a generic way, how to control your simulation and how to put basically some user interfaces on top of your simulation. And finally, we'll see how the current proposal stands up, what are the pros and the cons, and how we can proceed from there. So, what is my background? I'm working at Intel. I'm located in Eindhoven. I'm part of what is called the Silicon Hive team. And we develop tools to create cores and systems. And they're not just, let's say, cores like ARM cores or other microcontroller cores, but actually they are specialized cores for DSP type of applications, signal processing. So you could imagine domains like video coding, imaging, communications, etc. So those are specialized processors, heavily tuned towards the applications that are supposed to run on those processors. And then, yeah, what we have is tooling that's via some specialized languages to define the processors and the system. We offer a way for the users of our tools to easily create these processors and integrate them into systems. And what we also then produce for these systems are, of course, the tools which are needed to program these cores and to simulate and to generate hardware for these kind of systems. So, yeah, and like I said, the products that use our technology, they are normally multi-core. And what we see currently is that the number of cores that are used in these type of systems, they are heavily increasing. So what we are currently working on are products that employ, let's see, up to a recent example is 24 to 48 cores, which then on each course there are separate tasks running, and together they work together in some kind of synchronous data flow approach. Not always, the cores are not always the same, so it's a heterogeneous system. The cores are tuned to the tasks that are supposed to be running on those cores. And so you could imagine that some of these cores are have custom memories, they have special vector extensions, but only the cores that need those. What we use in our system simulation technology is standard SystemC TLM. And what we found out is that, what I also presented last year, is that there is no generic mechanism to support application software which runs on these cores. The debugging of that is not available in SystemC, in the reference implementation, and in the CCI, which we are supposed to use as a basic for our system simulation technology. And to show you the overview slide of the CCI, what has been identified as use cases for tools that are built on top of your simulation are system debug, analysis, altering, checkpointing, reverse simulation, etc. So I marked the system debug here as the use case that I'm heavily interested in. And what we then see is the standard interfaces, and we can point to the commands and the model information. It's just the built-in debug functionality. So what I think is that the topic of my presentation will cover these aspects, and therefore I think it's relevant for both the CCI and SystemC as well, the standard. So when I proceed to the problem statements, basically the point that we are starting from is actually our argument that system simulation with a number of core models, where n is larger than 1, needs support for multi-core debugging. And what we in our team mean with multi-core debugging is that we should be able to debug the tasks that run on each core separately and independently. And in our case, it means that we want to be able to attach a debugger, an application debugger, to the ISS model in the simulation that runs that particular task. So when we have a system that has n core models or n ISSs, we need to be able to attach n debuggers, each to a separate core, and each being able to debug the task running on that specific core. However, normal debuggers like GDB, they are not well suited for that, because they each assume that they will be in full control of whatever they are debugging. So we need to provide some extra capabilities in our system simulation and in the communication layer between the debuggers and the system simulation to be able to handle that. So that's why we came up with a list of requirements in order to support the use case that we want to support, and which our end users want to have. So we want to be able to simultaneously connect 0 to n debuggers, each to a separate core. And per attached debugger, we want to have all the debug functionality available, irrespectively if there was any other debugger connected to another core in the system at that moment in time. What we also want is we want non-intrusive debugging. So in case there is a breakpoint hit or an error triggered, or that you just want to interrupt the simulation because you want to know where you are in your application at that moment in time. You do a user break. You want to suspend the system simulation completely at the end of the current delta cycle. Also, you only want to continue when all of the debuggers agree that we should continue, because otherwise the debugger will get confused if it's still in break mode, and the system simulation would suddenly continue because another debugger had issued the continue command that would break the debugger. So therefore, we need to have a synchronization mechanism that we only continue when all of the debuggers have issued the continue command. When during simulation, the user thinks, I want to attach a debugger to the application which is running on a particular core, we want to suspend the simulation at that moment in time, such that the user can immediately inspect what the application is doing at that moment. And from that point on, he can continue, of course. When you detach your debugger from the simulation, you will want to continue. Basically, you want to remove it from the list of what I call simulation blockers. Yes, requirement number 7. When the system is in suspended state, so you already hit a breakpoint and you are debugging a task running on a particular core, and you want to see what the state is of another core, so you attach the debugger to that other core. You must be able to do so. This was not supported with the previous solution that I presented last year. We must be able to user break when the system is in a suspended state. That was also not possible with the previous solution. It must function with the official SystemC distribution. That was a specific requirement that we got, so we could not basically have a modified SystemC kernel and distribute that, because in some cases we also need to supply a model to a third party who wants to integrate it into its own SystemC simulation. So it has to work with the official SystemC distribution, or, and that we will come in the end of the presentation, in possibly an updated distribution which has some enhancements. And then there's an open topic that is still, let's say, more philosophical, is how to handle connections to and from other simulators in case of hybrid simulation, or how do these other simulators see that this part is suspended? For instance, how do we handle these situations? But we'll come to that later in the presentation. So the previous solution, as was discussed last year on the SystemC Evolution Day. So we have a parallel debug thread and a simulation thread, and the debug thread uses the boost ACO threads to handle multiple connections. In the previous solution, the simulation thread was completely locked when there was either an interrupt or user break or breakpoint hit. And in the implementation, we had some quite complex handling per ISS model of the step and run commands with locks, mutexes, and conditions, which was, on the retrospect, quite difficult to maintain and also to explain to other people. And we had one major disadvantage of that implementation, is that when the simulation thread is locked, we could not have new connections to the simulation and user break and other debug connections. That was not possible because it required a reaction from the model, which was not possible because the simulation thread was locked. So basically it prohibited inspection of application code on other cores when you had hit a breakpoint in one of your ISS models. So this was seen as rightfully a severe disadvantage of that approach. So what I had to conclude last year is that basically I needed to move the control on the SystemC thread, stop and continue, into some global, what I called debug service at that time, handling the pausing and or the resuming of the simulation. And I needed to keep an administration on core states and debuggers. So basically I had to know which cores had debuggers attached and which debuggers assumed that the core was in a broken state. So I had to keep count on that. And basically, if the SystemC thread was already stopped, I had to intercept the user break command from the from the debugger and continue only when all cores in broken state have received the continue command. So I had to keep the administration between what the debuggers expected, what the system simulation is supposed to do. I had to keep an accurate administration of that. And I'll come to that later on how I do that. Meanwhile, I looked at other approaches. There was an interesting one on suspend, unsuspend, and suspendable from Mark Burton in 2019 on the SystemC Evolution Day. What he did is he proposed an extension to the SystemC API. Basically, that would break requirement number 9 for me, because I was not allowed to use a non-official SystemC version. But still, there were some pretty interesting ideas there. I mean, he had the suspend all, unsuspend all, suspendable, unsuspendable concepts there. But yeah, his aim was primarily the synchronization of time between hybrid simulations and multiple OS processes. But there was, for me, one large problem with his approach, that using this async update request and the unsuspendable, suspendable concepts, he was still able to trigger a B transport from outside the system, basically temporarily unblocking the simulation. And that would break requirements 3 and 4 of my my list of requirements, because in that case, suppose I'm debugging the system and the application is running, it hits a breakpoint, so the simulation is broken. Using the concept which is presented here with the suspendable and unsuspendable, still the simulation state could change. Well, I would assume from the debugger's point of view that the system is broken. And that is something that what I gather from my end users is that they would really dislike. It could, for instance, mean that the view on the memory, I mean, you're currently inspecting a memory region and it could suddenly change because of this B transport, which was triggered from outside the system. So therefore, at the moment that I saw this, I thought, okay, I cannot use this concept at all. There are other approaches. I read some. Yeah, it's just one of several examples, but I read this thesis from Mr. Farkas regarding snapshotting. And there he used what's standard available in SystemC, the SC pause, to basically pause the simulation, doing his snapshotting, and later on doing the SC start again. And in his thesis, he mentions the possibility of snapshotting based on certain events and conditions. So when I saw that, I thought, hey, that is an interesting concept. Why don't I use the SC pause myself? So when you look in the standards in section 4.3.4.2 to be exact, there it states that, yeah, we can have SC pause, we can use this to cause the scheduler to cease execution at the end of current delta cycle, such that it can be resumed later. Which is exactly what I want. So basically, if on an application breakpoint hit in my ISS model, I can go to the paused state. I can later return. I can later resume the simulation using SC start. So that is what I'm going to use. There's, however, one note that SC start can only be called from within SC main. So there are some situations where it might not work out completely, but we'll come to that later. So if I now come to how I'm going to implement my synchronization control, I highlight in green the major difference now with my previous solution. I still have this parallel simulation control thread and simulation thread. I'm now going to use the SC pause to suspend simulation when required. And I will call SC start again to resume simulation. So that's basically when I have gotten the signal from all my attached debuggers that I can continue again. I need to have control over the SC main implementation. So that's for our own system simulations that we generate. That is no issue. We have that control. The simulation thread, that one is paused on condition in the target. So either an interrupt or user break or breakpoint hit or possibly an error condition. So when I have implemented this, the main loop in my simulation thread looks now a lot simpler than my previous solution. I only need one mutex and lock and one condition to interact with the simulation control thread. And when the simulation thread is paused, I can still do the new connections and the user break and other control connections, because I don't require a reaction from the model anymore. I handle that at a different place. So what is my synchronization control thread doing? It is responsible for the number of connections. So that basically that are the attached debuggers, and the number of simulation blockers. So I will increase the number of simulation blockers when I have when a debugger is attached, or when I have a user break command from a debugger. So when the number of simulation blockers becomes 1, I will pause or suspend the simulation. And I will send the correct response to the controller. If the simulation was already paused due to another debugger, I will create and send an artificial interrupted response to the newly attached debugger. And when I give the continue command in the debugger, I will decrease the number of simulation blockers and resume the simulation when it's 0 again. So only when the number of simulation blockers goes from 0 to 1, I will do the SC pause, and when this number of simulation blockers goes from 1 to 0, I will call the SC start again. And basically that's where the control logic is. So this is then the picture where all the logic is summarized. So still we have the parallel threads, the simulation control threads, which also has the session threads for each debug session. And each debug session has a separate debugger. And the simulation control thread knows how to basically talk to the models using a debug API. So if we look at this one in more detail, we have the synchronization control. It consists of the control sync thread and the simulation thread. We have all the connections, so the commands and the data to and from the debuggers, multiple ones in parallel. We have command handlers handling the commands sent from the debuggers, and those will forward the commands and get the data from the ISSs. But that's only for, let's say, what I would call the introspection commands, like looking at registers, looking at memories, etc. So when we have the control commands, the command handlers will interact with a control sync class, and that one will know when to start, resume the simulation again. Inside the ISSs, there's a main loop, which is just a simple while true execute. So execute all your instructions. If there's some condition, we will pause. So that will cause the scheduler to go to the SC paused state. So if we look at the different state machines from the boost connection, the protocol decoders, queue handlers, control sync, and the SystemC thread. So we go over them one by one. So on the left side, we see that there's a debug command coming in from the boost ASIO connection. So that one will basically forward it to the protocol decoder. That one will decode the command, insert it in the queue. If it's a normal command, if it's a user break, it gets special handling because it has to be able to intercept a running step or continue command. The queue handler will issue the command forward to the control sync. And the control sync has the states no blocker, basically, that In that case, it will start or resume the simulation. There's the state that there's one blocker. So it will go to that state when either there's a user break or a step run ended with breakpoint or error. And when there is more blockers, it goes to the end blockers state. So that's basically when there are more user breaks coming in from different debuggers and the simulation was already in the paused state. So when we have to transition to the one blocker state in the control sync class, we will pause the simulation. When there are additional user breaks coming in, we will increase the number of simulation blockers. When people issue a step or a continue command in the debugger, the number of simulation blockers will decrease again. And when it becomes 0, we go to the no blocker state. That's basically where we issue the SE start again. So, and in the SystemC start, you see the corresponding states from the SystemC scheduler. So basically, we go from SE running via SE pause to the paused state, and at some moment in time, we get the SE start from the control sync. And then we start running again. So what are we doing in our SC main? Basically, instead of directly calling SC start like you would do for a normal simulation, basically we create the additional thread for the debugger control, for our debug service, and we create the parallel thread for the system simulation. And in that thread, we will call SC start. And basically, yeah, we wait until the simulation finishes, and if we had allowed debug for this particular system simulation run, in the end, we also need to clean up the resources. So basically, we allow 2 different modes for a system simulation. So either you start it normally, and then you don't see any of these debug services at all. But you can also start with a special parameter, which sets the allow debug to true. And then you create all the other necessary infrastructure, which allows the debuggers to attach to the ISS models in your simulation. Well, the debug task is very simple. We have an IO service and we start it. So if you are interested in how to do such a thing, this is all standard things you can see in the Boost manuals. The simulation task, it's a little bit simplified, but this is how we implement it, basically. So what we do is it's loop. So while not stopped, we run the simulation. Stopped is basically a shortcut for seeing that we are in the SC stopped state. So if we finished the run sim invocation, then we see whether or not we are stopped or not. And if we're not stopped, we are waiting for the commands from the debugger. So if all the controllers want to continue, then we then we enter the loop again. So our run sim looks like this. We invoke SC start. If we come back from SC start, we notify the controllers and we return whether or not we are in paused state. So yeah, basically we implemented this and it works fine for our particular use cases. So, but it got me thinking, what if we use the previous concepts also for a simulation where we don't even have ISS models? And what if we apply the same ideas to, yeah, what I would call hybrid or distributed simulations? So in case of the simulations without ISS models, yeah, we need to have something like a generic system simulation controller. So I think, I mean, this is not a new concept. I mean, there have been, let's say, interfaces made on top of SystemC, which allows you to, let's say, run for a particular moment in time and then inspect what has happened, etc. But I'm not sure if we, let's say, should agree on a common API to do so. And what if we basically, because I mean, I have been concentrating on attaching application debuggers using GDB, RSP protocol to the ISS models in my simulations. But what if we could have, let's say, something like a remote CCI protocol, which has to be defined, of course, but I think it's an interesting topic to discuss whether or not there would be interest for something like that. And in the case of hybrid distributed simulations, how do we do what I would call state synchronization across multiple simulators? Basically, that is telling the other simulators that this part is currently in a suspended state, and not in a suspended state because we need it for, let's say, time synchronization or something like that, but because it is basically being debugged and not to be modified in any way. So yeah, this is just the simple idea that I had. I mean, just put a GUI on top of your simulation and have basic run, step, break commands. And since we have CCI, we should be able to inspect values that we are interested in our user interface. So, I mean, this is not shocking, I would say. This is pretty straightforward. The only thing is that if we want to have this in a generic way, we need to agree on how we do this run control, how we do the run and the step in a generic way. So maybe we should define an API for that. In the same way, we could do it using what I would call a remote UI. We would still have this control sync and simulation controllers in all of the simulations. But we need to have some way of connection handling there to a remote UI. And the remote UI should know how to basically attach to these simulations to know which simulations are running. So what if these purple boxes in your simulation would be able to fill some kind of database with simulation info, like this is the simulation which is running. This is the particular name, the configuration of this simulation. you can view it via this IP address and this port. So that would mean that you could start up your remote UI. You could see which simulations there are running on your cluster. And then select one of those to be able to basically inspect. And I mean, it would use concepts similar to what I have shown here before with the debugger connections, because I mean, that's also a remote connection. Yeah, the topic of hybrid or distributed simulation. I mean, if we assume that other simulators also have a similar paused state, how should we communicate or propagate the pause state from one part to the other parts? So if we control all of the parts, like the master simulators and the slave simulators ourselves, we could implement something like that we report the local simulation state changes in a slave simulator, for instance, to the master simulator. So basically we need to have some mechanism to maintain and distribute the global simulation state to slave simulators again. And this is the part which I which I highlighted in red. Basically, what if these are not all SystemC simulators, or we do not have control over SC main? Suppose that the part that we are responsible for, or we have control over, is just one of the slave simulators. In that case, how do we report back to either the master simulator or any of the other slave simulators that we are in this paused state? So currently I have no solution for that, but I think this is a topic that we need to address in order to make this this concept generic applicable. So what I came up with the idea of what I would call a state synchronizer. But as you can see, it is just an idea at this moment, no concrete implementation. So if we have this generic simulation control, how would it work? And then that is in the case where we would use basically some kind of CCI remote protocol. It would look a lot like what I presented for the GDB remote serial protocol. So we would, I imagine we would have a boost connection which would receive the data, a specific CCI command protocol decoder, the same queue handler. So we would have some form of CCI specific serialization and deserialization. We would have a control sync class which would know how to start and resume the simulation depending on how many blockers I would have. And we still would have the SystemC thread where we would need an additional control module which would handle the transitions from running to paused. So, and this is basically a run control API, which I propose for this generic SystemC module. And this is similar to what we use for our ISS models. So basically we have methods to handle the attach and the detach of a controller. We have methods for a step and a run on turn break and a user break to break the current run or step. And then, yeah, this is the main part of the main thread of this simulation control class. This one would basically wait until there's an attach event, which would mean there's a controller attaching to the simulation. And while we have the controller there, you would handle the different commands. So either if I'm in stepping mode, I would wait for the approximate amount of step time that was set. Or else I would wait until there is a detach event from the controller or a user break event from the controller, basically intercepting the current simulation. And if there's a controller still, I would basically invoke a method of my control sync to notify that simulation is going to pause mode, and then I would invoke the pause. So I'm going to my conclusion now. The current implementation that I have now using the SC pause mechanism, it implements all the requirements that I have discussed in the beginning. But we have the condition that we need control over the SC main implementation. And we don't require distributed and/or hybrid simulation scenarios. Yeah, so in case a model is integrated by someone else, then we cannot use this solution, not directly. I mean, unless we can convince that someone else to also modify his SC main implementation in the way that we do. There's even another case where we might not be able to use this solution, is that SC main is not even used. If you look at section 4.3.5 of the manual, it states that you can also run under direct control over the kernel of the kernel. So in that case, because then SC start and SC main is absent, we cannot use SC pause. So we would need some changes in SystemC, I would presume, unless I have overlooked something completely. So what I would like to do is to make my solution more complete, basically, is to extend the kernel scheduler state machine with an additional state, suspended. It's like SC paused, but it does not return to SC main. So that would solve one of the issues at least. And I would like to have some callbacks on the transitions to and from this SC suspended to enable messaging to other simulators. So that might solve the issues with, let's say, distributed and/or hybrid simulations. So for that, I would need to have some new API functions, which I would call SC start debug and SC end debug, which basically look a lot like the SC suspend all and SC unsuspend all, but with a more like a priority level. So setting this priority level would mean that you could not temporarily unsuspend the simulation again. So then basically that's my task for the coming year, is to adapt the implementation of what I called the control sync to use the new API in a similar way as the patch merged on the 21st of September, the unsuspendable patch by Mark Burton. And I do my work on top of that. So basically I need to refocus and prepare a patch. And this is what the proposed SystemC scheduler states would look like. And this is the end of my presentation. So any questions and discussion?
First of all, thanks, Peter. Thanks a lot. Very interesting. We have some minutes for questions. Yes. You have something written there, Peter. Perhaps you can see, but perhaps those have been resolved.
I need to go back to my Zoom. Oh, I stopped share now. Oh, there are a lot of things in the chat. I see. I completely missed that during my presentation. Let me go back.
I mean, it was who has been speaking? Mark, Jakob, myself. I don't have any specific question.
I think,
Jakob, do you have any question?
I think suggested something on slide 22, which might be a good idea to address. Did you also consider how to integrate hardware debug?
Yeah, but hardware debug is a
what do you mean hardware debug? Debug the actual simulator.
Don't look at me. This was Baz who asked it.
Okay.
Yeah.
Okay.
Can you hear me?
Yes, I can hear you.
I was just thinking there are some commercial simulators that have the option to intermingle SystemC debugging and RTL debugging. So you could set a breakpoint somewhere in RTL that says, hey, if this signal goes high, I want to stop my complete simulation. So I was just wondering whether your customers have such requirements that they integrate a number of Silicon Hive cores together with maybe some controller, but also with some custom hardware on their own side, which they want to debug from the RTL perspective in the environment of a complete system simulation.
Yeah, I think it might be done in a similar way. I'd have to look into the specifics on what kind of signals or what kind of conditions they would want to basically halt the simulation and do this and do the inspection. But I think using this generic application approach, we should be able to do so. I mean, you only need to basically be able to see the specific condition on which you want to go to this paused state. So that's, I think it can be done.
Yeah, okay, but so until now, not a request from someone to do this.
No, not at this moment.
But that's also slightly different, right? Because in that case, if you imagine you break in the RTL, it would actually I mean, that's different from breaking in target code like we're doing here. It's fundamentally different. Then you would have to stop the simulator, right? You would be calling out from SystemC into RTL, and it would just stop in the RTL. And I mean, you couldn't even inspect the state in SystemC, right? Because you wouldn't, you would be stuck in that call out, presumably. So mixing model debug and source code debug is kind of tricky in my experience.
Yeah, but for, let's say, simple setups, this has been implemented by commercial vendors. So for multi-gore SystemC, that's a different beast, I guess.
It depends what you mean by RTL debug at that point. It's not necessarily the case that there'd be a function call out.
I'm thinking that, Peter, when you mentioned that you could extend your approach to models that are not ISSs, I mean, then if it's a model that doesn't know of the concept of software, and if that model has a breakpoint, that I think means a breakpoint in hardware or in simulated hardware.
Yeah, that means a breakpoint in simulated hardware, and I guess it is a bit what you would see if you would mix that with, let's say, an application software debugger also attached at the same moment in time.
Yeah.
You would see in that application software debugger, you would see a message, at least that's how I implemented it at this moment, is that the system simulation has halted due to an external condition.
Yeah, like a register write on a non-memory mapped box, right?
Yeah, yes, but then you could, I mean, the way you could conceptualize that is to say that you are breaking that, so to speak, from the environment, right? You're not really breaking in the model code. What you're doing is breaking on the target system operation of having done a memory access, right?
Mm-hmm.
Just as if, I mean, to me, there's no difference whether a CPU issues a memory operation or some script code issues a memory operation. As long as you have the same memory subsystem, it's a job of the memory subsystem to capture that breakpoint. At least that's how we do it in SystemX.
Yeah.
We don't care if you do it from the command line or if you do it from target code, right? It's the same thing.
Yes, time is running. I thought it was interesting, Peter, to hear your usage of this SE pause, like as if it was sitting there just waiting for this use case to happen.
Yeah, and I was just wondering, I mean, I'm definitely not a SystemC kernel expert, but I was just wondering who invented the SC pause and for what reason was it there?
I think originally it was kind of similar to what you're suggesting, but it's the issue is, as you've pointed out, kind of doesn't work out quite the way you want it to, because you have to be in charge of SC main, which a lot of us are not.
Yes, and so therefore I was thinking, but why was it done in the way that it's? I mean, yeah. And from one hand, it is useful and it is exactly what I would like to have, but it has this limitation which I don't really understand.
Yeah,
so I'm not sure about the history of these state transitions and why it has been done like this, but.
To be clear on the actual proposal on what you're suggesting, then effectively what you're going to be suggesting, we assume over the next 12 months, is to augment the current suspendable type interface with an additional parameter, which would then give you a priority. And that's kind of where we're going to, isn't it?
That would be my idea, yes. And then also that when you do that, you go to this SC suspended state, so such that from the outside you could see that you are actually suspended. If you
that would be the other thing that would be nice to augment that API with something which at least tells you oh, by the way, you are now suspended. Because at the moment that you can't find that out.